Welcome to this video on chemical equilibrium systems, principles, and applications. I am Dr. Luis Bello, and you can reach me at the email shown on the screen. We begin with an introduction to chemical equilibrium. This is defined by the balance between the forward and reverse reactions, where the macroscopic properties remain constant, though changes occur at a microscopic level. The dynamic nature of equilibrium highlights that reactions are simultaneous. At equilibrium, the rates of the forward and reverse reactions are equal, involving continuous molecular motion and collisions. Next, we will discuss equilibrium expressions. Equilibrium expressions quantify the relative amounts of reactants and products at equilibrium. The reaction quotient, Q, is a concept closely related to the equilibrium constant. The reaction quotient helps predict the direction a reversible reaction will shift to reach equilibrium. We use the reaction quotient to determine if a system is at equilibrium or if it needs to shift towards products or reactants. Understanding the equilibrium constant, K, is fundamental to chemical equilibrium systems. Homogeneous equilibria involve reactions in a single phase, such as gas phase or solution phase examples. Learning to write the K_C expressions for these systems is key. Heterogeneous equilibria involve multi-phase systems, including pure solids and liquids. The role of phase boundaries is important, and K_C expressions are simplified by excluding pure solids and liquids. We will explore how changes in pressure affect equilibrium systems. Concentration calculations are essential for solving equilibrium problems. This involves setting up initial change in equilibrium, or ICE, tables to track concentrations. Understanding how to determine the change in concentration, often represented by X, is a crucial step. We use the equilibrium expression and the equilibrium concentrations to solve for K or for unknown concentrations. The ICE table method provides a structured approach to solving these problems systematically. Calculating equilibrium concentrations often involves solving quadratic equations. In some cases, approximations can simplify the mathematical calculations. Equilibrium constants are affected by temperature, but not by pressure or the presence of a catalyst. They have specific units and significant meaning. The magnitude of K tells us about the reaction's extent. Large K values indicate product-favored reactions, while small k values indicate reactant-favored reactions. Applications of K include predicting reaction direction, understanding industrial and biological processes, and studying environmental equilibria. Our problem-solving strategy involves setting up equilibrium expressions and using ICE tables. We'll also cover common approximations and the necessary assumption checks. We will review common mistakes, such as incorrectly including solids or liquids in the K_C expression, and unit consistency, mathematical errors, and sign conventions. Real-world applications of equilibrium include industrial synthesis, blood pH regulation, ocean acidification, and atmospheric chemistry. Practice problems for homogeneous equilibria cover gas phase reactions, solution equilibria, and multiple equilibria, with step-by-step solutions provided. Practice problems for heterogeneous equilibria include solid gas and precipitation reactions, solubility equilibria, and complex formation. Advanced concepts involve multiple equilibria systems and the effects of temperature, pressure, and volume changes on these systems. Finally, we discuss equilibrium disturbance and Le Châtelier's principle, focusing on how concentration, temperature, and pressure or volume changes affect the equilibrium position.